Good morning, everyone. Welcome back to Organic Chemistry 1. Before we get started on today's lecture, I have a couple of announcements to make. I don't know if everyone noticed, but at the time of this recording, earlier today, I posted the solutions for Exam 1 and Quiz 1 and Quiz 2. So for you, this would have been yesterday, but for me, I did it this morning. Anyway, so make sure you go through those. I already explained this in the exam solutions video, but all you'll get is the video so that you can see how to work the problems on the exam and on the quizzes. Because I feel like you get the best practice by actually writing out those things on the exam, like the problem and the answer. So, and if you need to stop the video and pause it so you can write it down, so be it. But that's the way we're going to do the exam and quiz solutions videos. That being said, somebody in the class actually asked me to make the quiz solutions available, and so I didn't think about that before, but I've thought about it now. And so from now on, after we complete a quiz, it's due and it's been graded and everybody's taken it, I'll post a solutions video for the quiz, so you can use those videos to study for the upcoming exams as well. As for our Exam 1 and Quiz 1 and Quiz 2, you can use those to study for the final exam, because I promise you it will be cumulative. So that's how that's going to go. And so make sure you go through and watch those videos. Second announcement is that I have decided that, and I've said this in the exam video as well, but just to be clear, I have decided that for the first exam, I will give everyone a 16-point curve. That's 1-6. And what that means then is if you, for example, got an 84 as your score, then you'll end up getting 100 for your score, percentage-wise. And so I haven't gone through and updated the scores yet, but I will today and tomorrow. And I also will go through and finish grading up all your labs as well, your lab reports. That being said, the second announcement is that it's about lab. Don't forget that today you do have a lab to do, so go over to the lab flow, check it out. There'll be a pre-lab video for that. And then also, this is another reminder, your lab midterm will be next Monday. Sorry, not Monday. We have lab on Tuesdays. Next Tuesday. So make sure you're prepared for that. The information will come straight from the reports and that you've been doing and the videos. And so, as a suggestion for studying for the midterm, I would watch the videos over and over again, which is easy because they're short. They're not long-winded like my videos are. But then also the PDF that has that background information on it and all the questions on it. That's what you need to study for the final exam, because that's where, for both the final exam and the midterm. But the midterm will be next Monday. So be prepared for that. Okay, so that's it for the announcements. You have any questions, just let me know. Again, I have office hours on Tuesdays and Thursdays from 4 to 5. A number of people have already scheduled times during my office hours to get help and to talk and stuff. So I might not have time. I will have time because I'll be on Teams, but I'll be like in conference with other students. So if you can't get a hold of me during Teams office hours, just email me and we can schedule another time. Okay. All right, let's get started. Okay, so today is lecture 5, and let me go ahead and change the video for you here, or the feed, so that you can see the PowerPoint. There it goes. And today we're going to be talking about alkanes. So this will be the first lecture in which we start actually getting into some organic molecules, classes of organic molecules, and functional groups, and actually learning about their reactivities, their properties, and such. The first one is alkanes, right? Which you can probably guess that alkanes are the most simplest hydrocarbons, right? Hydrocarbons meaning compounds that are composed of only hydrogen and carbon, right? So we have ethane there, we have ethylene there, and we have acetylene, right? Those are the single bond, double bond, and triple bond versions of two carbon hydrocarbons, right? And then we've talked about this one before, where we had benzene here, also known as phenyl, right? We call it a phenyl ring too, but that's a benzene ring, and literally that's just a cyclohexane, right? That is conjugated bonds, right? It's got double bonds on every other bond, right? So the thing to note here is that a hydrocarbon is saturated when every single carbon is filled up in bonds with hydrogens, right? And unsaturated, right, is a hydrocarbon is one that has at least one carbon that has a double bond, right? And so it's missing some hydrogens. So that would be true of ethylene, and it would be true of acetylene, and that would be also true of benzene, right? And this comes into play a lot in in biochemistry when we talk about fatty acids, right? Because saturated fatty acids are, for example, for the most common one that our body makes is called palmitate or palmitic acid, and it is a 16 carbon fatty acid, right? So basically 16 hydrocarbons in a row. I'm not going to count it out, but 16 of those, right? And then that. So that's like and I might have miscounted there, but I'm just going to write there, that's 16 carbons, okay? So there's no confusion when you're watching the video. So if there's 16 carbons there, and then there's a carboxylic acid like that, right? That functional group, then that's palmitic acid, right? And that's the most common fatty acid that's made by your body. But palmitic acid actually is a saturated fatty acid because every one of those carbons has a hydrogen on it, the most it can, right? So the end carbon has 3 hydrogens on it, and all the ones in between have 2 hydrogens on it. That's saturated, okay? Saturated fatty acids are solid at room temperature, like butter, things like that, or beef tallow, which is just beef fat, right? If you didn't know this, there's a secret to making awesome brisket, right? And a lot of people wonder, like, how do you get brisket to be super moist but also very tender, but then smoke it for like 18 hours and it's still dry, and how do you make that tender? Well, the secret is to cover that brisket with as much beef tallow, which is fat, beef fat, rendered beef fat, as much as you can, right? Like, when I do it, I'll put in the brisket for a few hours, and then I'll take it out, spray on some beef tallow, put it back in the smoker, and then after that, when it's done, when it reaches like I believe the temperature I get it to is like 203 degrees Fahrenheit, I'll pull it out, spray on some more beef tallow there, because it's got to be warm beef tallow, otherwise it's a solid. Spray on some more beef tallow on there, right, and wrap it up and let it sit there for a couple hours while it's cooling down. That is some really good brisket right there. That's some tender, that's some tender brisket right there. Anyway, so yeah, that's the difference between a saturated and unsaturated fat. Didn't know I was going to get into a barbecue smoking rant there, or wait, what's the good version, rant or rave? I think rave is good. A barbecue smoking rave there. So many organic compounds have common names, of course, because we organic chemists they come up with names for things when they find them out. But then, they're like, oh crap, there's a lot of molecules and they're very similar to each other, and then so, we have to come up with a system for naming. But before that, and we'll talk about that system in a minute. But before that, that was crazy. My little dog here, Kovu, just figured out how to open the door to the study. Crazy guy. Anyway, he's walking around, and and he's shaking. Anyway, so it was just raining, right? It was like storming like crazy like a few minutes ago, and he was not having a good day. So I guess that's why he wanted to come into the study. He's like a small dog, so I don't know how he was able to open the door just now. That's a little weird. Sorry, back to what I was saying before. So chemists, back in the day, they really, they were naming molecules as they found them. For example, this guy Adolf von Baer, he's the founder of Bayer Pharmaceuticals. He named barbituric acid here after a woman named Barbara, which it's my head's blocking right there, but it literally says a woman named Barbara. I don't know who Barbara is. Maybe she was very special to good old Adolf von Baer there, but that's how he named it. So before, we'll talk about the naming system later for organic chemicals, in the lecture. But back in the day, though, everything was named after the chemists named it after whatever they wanted to, whoever discovered the molecule. So then we have formic acid here, right? Formic acid was isolated from ants and named after the Latin word formica for ant, right? Uh, that's where the formic acid comes from. Urea was isolated from urine, so they called it urea, right? And then we have morphine here. Morphine is a painkiller named after the Greek god of dreams, Morpheus. Interesting, right? Interesting. That's morphine for you, right? And morphine sure does make you feel good when you're feeling bad, you know. So there's gonna be a lot of them. Another one that's common too is muriatic acid. I'm pretty sure muriatic acid is hydrochloric acid. And honestly, I didn't know it was named muriatic acid like ever until I watched a show back in the day on Animal Planet when they were saving like whales or something like that. Whale Wars, maybe that was the name of the show. Comment down below in the comments if you're watching this on YouTube if I'm right. But I think it was called Whale Wars, and they would throw like bottles of muriatic, like they didn't have weapons, right? They weren't like they were on big ships, but they had a fleet, but they didn't have weapons. So the way they would combat like whalers was by throwing bottles of muriatic acid on their ships to spoil the whale meat. And I'm pretty sure that's hydrochloric acid. Again, correct me if I'm wrong. Post it down below if you're watching this on YouTube. So the system that we use to I'm going to turn off my phone real quick. It's been going off a lot today. The system that we use to name alkanes and all other organic molecules, right, is called the IUPAC system. Systematic naming of compounds. This includes the parent name, the name of substituents, and the location of the substituents. And you'll see that in the upcoming slides. What does IUPAC stand for? I can't remember. International. I know the first one is international. The last letter is chemist. You know what? Let's just look it up on YouTube real quick. Not YouTube, Google real quick. Let's Google it. IUPAC. And see, this should just make you feel better about not knowing everything, absolutely everything about organic chemistry, because nobody can. And for me, I don't think that you should have to memorize anything that you can look up immediately. And the the acronym IUPAC is not one of those things that I think you need to memorize. So, yes, here we go. IUPAC stands for the International Union of Pure and Applied Chemists. I never would have figured that out. Never would have figured it out, right? International Union of Pure and Applied Chemists. Good times. Good times. You don't need to know that. I was just curious. So, let's start going through some rules about naming alkanes, okay? The first rule is identify the parent chain. The parent chain is the longest consecutive chain of carbons. So when you're looking at this monstrosity here, right, its parent chain is the longest chain, so it's the one that you see in the red line here, which I won't draw over it because it's already drawn. Okay, it's already drawn for you. But you know it's longest chain because it has 1, 2, 3, 4, 5, 6, 7, 8, 9 carbons. If you were to try to get a long chain by tracing any other route on those carbons, you'd have less than 9. So 9 carbons is the parent chain. So the parent chain gives you the name of the actual molecule itself, right? So here's a situation in which if there's more than one possible parent chain, choose the one with the most substituents attached, right? So you could choose this one here, where when you draw this long chain, okay, and you have 3 substituents, this ethyl group, and this methyl group, or you could pick this one here, where there's just an ethyl group and a propyl group, right? A propyl group. So what's going to be the correct one? It will be the one with the most substituents on it, 3 substituents, okay? So once you figure out that number of carbons in the longest chain, known as the parent chain, you can name the chain after some Greek prefixes, or maybe it's Latin, maybe it's both. Um, but for example, meth means one carbon, right? So for example, methane, which is CH4, okay, or eth here, which is ethane. That's two carbons, right? So that's CH2, CH 6. I have to think about that for a second, right? CH6. Is that right? Yeah, that's right. Okay. Then propyl. Oh, sorry, not propyl. That's propyl is something else. I apologize. It's actually. Oh well, you know what I did there. I can't remember what I did there. Anyway, I said propyl was something else over there on the previous page, and I think I'm right about that. So let's just keep going. Prop is propane, which is 3 carbons. Bute is 4 carbons, like butane, right? That's this here. That's butane. Pent for 5. Oh, that's where the Greek starts. And that's 5 carbons, like pentane. Hex is 6 for hexane. Hept for heptane, which is 7 carbons. Oct for octane. 8. Non for nonane, and that was the one that we did previously in the previous slide. It had 9 carbons, so that would be a nonane. 10 for decane, right? Which makes sense. Undecane is 11. Dodec, or dodecane, is 12. Tridec, or tridecane, for tridecane is 13. Tetradec is 14. So this is how you know that it's both Latin and Greek, right? Because tetra is actually the definition for, not the definition, that means 4 in Greek, right? But then you go over here, the previous slide, and oop, I went too far. And 4 is actually bute here, right? So, you know, that's how you know it's like 2 different languages going here. Oh, organic chem, that's why they gotta be so complicated about it. Anyway, so tetradecane, 14 carbons. Pentadecane, pentadec for 15. Icos, right? That's 20, right? And so icosane, which is 20 carbons. And if you don't remember how to say that, or you don't remember what that is, just remember that an icosahedron, right, is a shape with 20 sides, right? A icosahedron. And then ooh, that's weird. Triacont. Triacont? I've never actually had to say that before. Triacont. So triacontane. Let me know in the comments below if you're watching this on YouTube if I'm even saying that right. That's 30 carbons. Tetracont, which is tetracontane, 40 carbons. Pentacont, pentacontane, 50 carbons. And then hect, which is hectane for 100 carbons, right? So we also have cyclic compounds, right? Like I was talking about before, that benzene ring is basically a cyclohexane, which is a cyclic hexane that has double bonds in it, right? Conjugated. So identify the parent chain, the longest consecutive carbons. If the parent is a cyclic, then add the cyclo in front of it. For example, we have cyclopropane here, which is a triangle, or 3 carbons in a triangle shape. We have cyclobutane, right? 4 carbons connected to each other in a cyclo. And then cyclopentane, which is 5 carbons, right? Cyclopentane in a cycle. So another plug for Wiley Plus here. Make sure you're going over there and practicing Skill Builder 4.1 for identifying the parent chain carbons, right? So let's see if we can identify this. All you have to do here is identify the longest chain, okay? And you'll be able to just pick, excuse me again. We don't want to run before we can walk here, so let's just identify the parent chain and name its parent chain, okay? So if I look at this one here, 1, 2, 3, 4, 5, 6. All right, that's 6 carbons if I go that way. 1, 2, 3, 4. It's only 4 carbons if I go that way. It's 5 carbons if I go that way. Right? So the one that's up here is the correct one, so that's a hexane for its parent. Okay? This one right here is actually symmetrical on both sides, right? So it doesn't matter if you go this way or that way. So it would be 1, 2, 3, 4, 5, 6, 7. I could go that way. That's 7. Or I could go 1, 2, 3, 4, 5. Right? So which one is it? It's going to be the one that's over here. So that's going to be heptane for its parent. Okay? Heptane for its parent. And then for this guy here, it's cyclo. 1, 2, 3, 4, 5, 6, 7. So that's a cycloheptane. Right? Cycloheptane. And you might be asking yourself, what about those 2 methyls there? Well, that's when you write stuff like 2 methyl heptane, you know, or that's weird. 2. My dogs are getting upset about something. I have no idea what. 2 methyl cycloheptane, right? But there's 2 methyls there, so it would actually be 2 methyl cycloheptane, right? Sorry, I'm skipping ahead. Let's keep going. Walk before you run. So, identify and name the substituents, right? Well, we already did this before, right? We have here 2 carbons, so that's a ethyl group right there, right? And then this substituent here, right, that's 3 carbons, that's a propyl group. And then this here is just the methyl group because there's only 1 carbon. So remember that the parent chain is the longest chain, and then substituents are anything that comes off of that parent chain, okay? So you name the parent chain, you know, whatever the number of carbons it is. So for this one it would be 1, 2, 3, I miscounted again, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So, right? So that's a decane, right? And then you have the substituents are on there too. So that we already named before. And I don't want to skip ahead. I'm turning a new leaf, and I'm trying to not talk about things before it comes up in the lecture, because it happens a lot, right? Get on this roll and just start yapping. Okay. So next, now you can identify and name the substituents. Oh, see, I just did it. I just said I'm turning a new leaf and trying not to jump ahead, and I just jumped ahead. So we have the methyl group there, we have the propyl group there, and then we have the methyl group there. So the moral of this slide is that when you have a substituent, the Greek word for the number ends in il, right? Like propyl instead of ane, like dodecane or decane, right? Okay. I'm trying really hard, guys. I'm trying really hard. All right, so a ring can either be a parent chain or a substituent depending on the number of carbons, right? So here, the substituent has 3 carbons, but the parent has 6 carbons. So this is quite obviously propyl cyclohexane because the parent has more carbons in it. Okay? Then for this one, we have a cyclopropyl. Yes, that's a cyclopropyl because there's 3 carbons there, right? But the parent here has 4 carbons. So that would be then 1 cyclopropyl for the triangle, right? Butane for the parent, which is 4 carbons long, right? And the 1 just comes from its 1 position, right? Which means the first carbon. There are rules for that too, right? But for this one, it's just a butane, so the butane is the same on both sides, right? So it's one carbon one. And actually, I'll clear that out just so I can say that one carbon, carbon two, carbon three, and carbon four. Right? That's how you name them, just in a row. And you can see that this rule here is saying that the one with the substituent is the carbon with the substituent, or the substituent closest to the end is the one that you will name. You will go in order with 1, 2, 3, 4, right? So that's why it's 1, 2, 3, 4. Okay, practice with Skill Builder 4.2. Another plug for Y Plus. Make sure you go over there. Identifying and naming substituents. Ooh, branches. Okay. For substituents with complex branches, right? Number the longest chain carbon within the substituent. Start with the carbon attached to the parent chain. Name the substituent. In this case, it's a butyl, right? Because we have 4 carbons here. Okay. And then name the substituent's side group, right? And in this case, it's a methyl, and it's on the second carbon, so it's a 2-methyl, right? So we have here a butyl with a methyl attached to the second carbon on the substituent, right? The branching substituent here, right? But then don't forget that we have, so that would be, so just that part alone, right, is the 2-methyl butyl part, okay? Then we still have the 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 carbons, which is interesting because it's going to be symmetrical on both sides, which means it doesn't matter which side we start the carbon on, right? So it would be carbon 1, 2, 3, 4, 5, 6, right? So it would be the answer, the name of this entire molecule would be 6 2-methyl-butyl, and I forgot what 11 was. Undecane, right? Okay. So, propyl branches. Oh, good. See, there's a propyl. That was the thing I was thinking about before when I said I named something propyl, but I wasn't sure what it was. That is a propyl. What I named in the previous slide. But the thing that I forgot to do is put the iso in front of it, right? So when it looks like a little triangle thing like that, it's iso, right? So here's your parent molecule right here, right? Your parent carbon chain, and then your substituent here. When it has just 3 carbons in a straight chain, it's a propyl. But when it has 3 carbons that are branched like that, right? It's still 3 carbons. It's the iso. The isopropyl, right? Isopropyl. Also known as the 1-methyl-ethyl, right? Which makes sense, right? Why is it 1-methyl-ethyl? Well, because IUPAC says you can name this carbon 1, carbon 2. That makes the ethyl part because it's 2 carbons. And then on the first carbon, right, there's a methyl group, 1-methyl-ethyl. But we all call it isopropyl, right? Just like a good example of it would be isopropanol, the thing that we needed so much during the pandemic and was absolutely impossible to buy. There's tons of it now, right? But during the pandemic, we had a shortage of isopropyl alcohol, which looks like this, right, to kill some germs, right? And so, our breweries stepped up and started letting us, sanitize our hands and our tables and everything with drinking alcohol instead. So, But hey, today, there's plenty of isopropyl and ethanol all over the place. So, we're going to need it for the recovery. Not the isopropyl. You don't want to drink that. That's bad. Okay? All right. So here's some more branches that have like common names. You've heard me use these words before. So we have a parent chain and a substituent is attached to it with 4 carbons. Of course, it's called a butyl, right? But then if it's shaped like this, where you have one branched off methyl and then a branched off ethyl, right? It's called a sec butyl, right? You can also call it 1-methylpropyl because you have a propyl because it's 3 carbons long, and then the first carbon has a methyl, uh, um, uh, a methyl group coming off of it. Sorry, right? This is the methyl group that we're talking about, right? And this part right here is the propyl group, right? So we also have the isobutyl, right? Very similar to the isopropyl, and we can also call it 2-methylpropyl, right? Because here we have a propyl because there's 1, 2, 3 carbons, right? And on the second carbon, right there, is a methyl group. But it's easier just to call it isobutyl, right? You can go with the common name, or you can go with the IUPAC name, systematic name, whatever, right? And I won't care. They're both the same to me. And then before we had a lot of tert-butyls, right? Remember I had that tert-butyl alcohol, the tert-butoxide, when we're talking about acids and bases and pushing electrons and stuff. And so tert-butyl looks like a little talon, little bird talon, not talon, not that part is the foot, bird foot, chicken's foot, right? And we can call this 1,1-dimethyl ethyl, right? Why is it 1,1-dimethyl ethyl? Because you have your first carbon here, right? And you have your second carbon there, for example, and that makes an ethyl group. Since this is your first carbon, and then you have 2 methyls attached to the first carbon, right? That's 1,1 for the first carbon, dimethyl because there's 2 methyls, right? And ethyl for the 2 carbon parent chain, or this 2 carbons right here, right? Oh, and then I had a slide previously that I said it was what was it? I said 2,2-methyl heptane. The cycloheptane, the one with the cycloheptane, the 7 carbons in a ring, and then 2 methyl groups coming off it. I forgot to say I forgot the di part, right? Which is 2,2-dimethyl cycloheptane. Okay. Practice naming. Obviously, I need it. I forget stuff too. Skill Builder 4.3. Identifying, naming, substituents. Try it out. It's on Wiley Plus, right? It's on Wiley Plus. You'll get to this point where you just know these names, and then you don't use the systematic name anymore. Like you actually figure it out, and so you start it becomes pretty intuitive, and you only make mistakes 90% of the time when you start just knowing these names off the top of your head. You should still use the systematic IUPAC way though, just so you can do the best you can in this class. Okay, the best you can. All right, so assembling the IUPAC name and the introduction. I don't know why I wrote that all out there, but I guess in this part we're about to put it all together. Everything we just learned, I guess, right? Carbons in the parent chain have been numbered, right? And then so we have 2 examples here. We have 2-methylpentane here and 3-methylpentane here. And I feel like this is a slide one of those slides where I already spoke about it before, and it just shows up kind of delayed. But here we have a 2-methylpentane, right? Because the methyl group's coming off of the second carbon, and here we have a 3-methylpentane because it's coming off of the third carbon. Okay. 2-methylpentane means that there's a methyl group on the second carbon of the pentane chain, right? And the same is true of the third carbon. That would be 3-methylpentane. I wonder why they didn't put another bullet down there for 3-methylpentane. Seems a little bit discriminatory, honestly. Maybe I should write it out. No, that would waste time. Let's keep going. Here we go. Guidelines to follow when numbering the parent chain. If one of the substituents is present, number the parent chain so that the substituent has the lowest number possible. And that's what I was saying before, right? When you have a substituent on a chain and you're trying to name or number the carbons, you want to make it so that the substituent is closest to the end where it's got the lowest numbered carbon, right? So here we have a heptane, and the methyl group is on the second carbon there. So it would be 2-methylheptane, right? This would be incorrect because here, if you numbered it backwards, it would be in the 6th carbon, And 6-methyl heptane wouldn't make any sense because it violates the rule, right? You want it to be closest to the end, so this is the guy that you want, right? That's how you want to name them, the parent chains. More guidelines to follow. When multiple substituents are present, number the parent chain to give the first substituent the lowest number possible, right? So again, here, the first substituent here is the methyl group on this heptane, right? So we already learned in the last slide, and me just rambling a few slides ago, right, that it's going to be the 2-methyl because 6-methyl is just too far away from the lowest end, right? The lowest number carbon. So the 2-methyl is good, right? And then the next thing you need to do is figure out the second substituents, which is these guys right here, right? These guys are the second substituents, right? And you name them based on the first substituent. So since you've already picked this as the one that you want to use, because it's correct, the 2-methyl heptane part, then the 2 methyls here, right, are going to be on carbon 5, right? So 2 beats 3, and that's why it's going to be 2,5,5, right? Instead of 3,3,6, which is the 2 methyl groups on the third carbon first, and then the last one on the 6th carbon, right? In this case, this one's correct because your closest one to the end has got the lowest number, and then the other two methyl groups are attached to the 5, right? So this would be something like heptane, right? So 2-methyl 5,5-dimethyl heptane, right? Cool stuff. Let's try this again. If there's a tie, then number the parent chain so that the second substituent gets the lowest number possible, right? So here we go. There's a tie here. These are the same, right? Those are the same. So that's a tie. They both have methyl groups, one away from the end on each side. So now it comes down to the second substituent group. And here, the second substituent group has the lowest number because it's on the third carbon. So that's why you would say 2,3,6, right? Second carbon, third carbon, and then the last methyl group on the 6th carbon. This is wrong. Okay. Then, if there is no tiebreaker, then assign the lowest number alphabetically. Okay. So here we have a pentane with a bromine and a chlorine on it, right? So it's like one bromochloropentane or something like that, right? But the question then is, do you say one bromochloropentane, or do you say one chlorobromopentane, right? Well, you would say one bromo because this rule says that you use the lowest alphabetically, which B is alphabetically, before A. B is alphabetically before C, so bromo goes first, right? Then the same rules apply to cycloalkanes, right? Here we have the correct version because, right, we have the 1, 2, 3, and the first carbon has 2 substituents, right? And the third carbon has 1 substituent, right? Here, the first carbon has 1 substituent, and the third carbon has 2 substituents. So 1 in the middle here beats 3, right? So 1, 1, 3. Good stuff. Whew. Naming just wears you out, doesn't it? So, to assemble the complete name, put the number and the name of each substituent before the parent chain, right, in alphabetical order, which you've heard me do that before several times in the slides. The prefix is used di, tri, tetra, penta, etc. if multiple substituents are identical. Note di or tri is ignored when alphabetizing substituents. Okay? So you don't have to you don't have to do the die or try when you're not using any of the other ones and you're only using the alphabet, uh, uh, the alphabetizing of the substituents to be the way you name it, right? So here's a summary on how you name alkanes, right? First, identify the parent chain. Next, identify and name the substituents. Then name the parent chain. Assign the locant to each substituent, right, or the location of it on the carbon chain to each substituent. Then list the number of substituents before the parent name in alphabetical order. So, practice. Skill Builder 4.4, right, on Wiley Plus. All right, following the rules, we can name the following compound, right? We already know that this is a cyclohexane because there's a 1, 2, 3, 4, 5, 6. That's cyclohexane, right? Okay. We have some substituents. Let's name some substituents. We have a tert butyl right here, right? Then we have an ethyl right here. Then we have two methyl groups right here, right? Two methyl groups. Okay. You can also call that a 4,4-dimethyl, right? Because they're on the fourth carbon. So you bring it all together and you get one tert butyl, right? Two ethyl, 4,4-dimethyl, right? Cyclohexane. Good times naming that molecule. Good times. Ooh, just when you thought it was getting complicated or getting a little bit simpler, right? Now we have bicyclic compounds because you can have an alkane that's bicyclic, right? Where you have a 5-membered ring here, but then you can also have a 5-membered ring over here. Okay. So when you flatten that out, it looks like this guy here, right? So here's your first 5-membered ring. Right? It almost looks like one of those optical illusions. And then here's your other 5-membered ring. Right? So you have two 5-membered rings. To name a bicyclic compound, include the prefix bicyclo in front of the parent name. Right? It sounds simple enough. Okay. Naming bicyclic compounds. The bridgehead carbons. Okay? The two carbons where the rings are fused are bridged carbons. Alright? So that's these guys right here. These, there are 3 paths connecting the bridgeheads, right? Which makes sense because it's like a triangle. 1, 2, 3, right? Not a triangle, but like a purple. Count the number of carbons on each path to name the compound, right? So here, well, this is a heptane, so let's just keep on using the pentane first since we've been working on the pentane up until now. This would be bicyclo-2,2-pentane, right? Because we have, 2,2,1-pentane, right? Because on one side of the ring we have 2 carbons, right? And on the other side of the ring we have 2 carbons. So that's this 2 and this 2, right? And then on the top of the ring we only have 1 carbon. That's why it's bicyclo-2,2,1-pentane. Right, yes. So let's look at the heptane now, right? There's a bridge. These are the bridging carbons of the heptane right here, right? And that's where you start the numbering from. Cycloheptane, right? So there is 3,1,1 heptane. Bicyclo-3,1,1 heptane, because on one side of the bridge there is 1, 2, 3 carbons. And then there's only 1 carbon here at the top of that bridge, and at the bottom of that bridge there's only 1 carbon there. So it's a bicyclo-3,1,1 heptane. Practice with Skill Builder 4.5 on Wiley Plus for more practice. Okay. Ooh, back to isomers. Isomers. Back to isomers. I was saying the word isomerization, but that's not what we're doing. It's just isomers. So recall that isomers have different structures with the same molecular formula, and constitutional isomers have different connectivity of the atoms. Okay, different connectivity of the atoms. So here we have a 1, 2, 3, 4, 5, 6. So that's a hexane. Ooh, hexase. That's terrible. Hexane. But we also have 1, 2, 3, 4. 1, 2, 3, 4, 5, 6. Right? So that's also a 6 carbon. 6 carbon hydrocarbon. Right? So both of these would be constitutional isomers because they have the same number of carbons and hydrogens. Okay? Same number of carbon and hydrogen. We can actually name this guy 1, 2, 3, 4, 5. So that would be a pentane. Okay, that would be a pentane. And on the second carbon, there's a methyl group. So that would be 2-methylpentane. 2-methylpentane is a constitutional isomer of hexane. Good times, good times. I promise you, it's a good time. I may be yawning, but it's a good time. It's been a very rainy day today, so it just now started getting sunny. I feel like I need to jump in the pool because it's hot now. All this humidity out there from all the rain. You know, it was like a monsoon came through a couple days ago. I mean, a couple hours ago. So yeah, next. Constitutional isomers, many possible, right? As the number of atom carbons increases, the number of constitutional isomers increases, right? So that makes sense because the more different connections you can make with the different carbons, right? So here we have a propane, and it's got one constitutional isomer. But let's just jump all the way down to a dodecane, that's 20, a decane, and you have 75 different constitutional isomers. Fun stuff. Go build them. I'm just kidding. You don't have to do that. How to recognize them, those constitutional isomers, right? Being able to recognize different structures as either being isomers or being the same compound, right? So interestingly enough, all these are constitutional isomers right here. But if you look at this guy here and this guy here, they're actually not constitutional isomers. They're actually the same molecule, right? One is just bent like this, right? And we'll learn more technical words for it in a minute. But one is bent like this and the other is bent like this. Right? But they're actually the same. Okay? You can test if structures are the same in two ways. Flip one of the molecules in 3D space and rotate around its single bond until it's superimposable on the other molecule. Name them. If you name the IUPAC name, if they have the same IUPAC name, then they're the same compound, right? So we're actually going to talk about that a lot later too. It being superimposable and you being able to rotate around a single bond or a sigma bond. Spoiler alert: you can rotate around a single bond or a sigma bond, but you can't rotate around a double bond or a pi bond, right? Which kind of makes sense because a pi bond's like this, right? And how do you can't do that? That doesn't spin. But if you are a single bond like this, you can just rotate like craziness. Okay, good stuff. That has actually a lot of implications in biochemistry because remember, we were talking about the amide bond for resonance and the nitrogen on the amide bond, which is actually the same bond that is between every single amino acid that is in the proteins that function in your body. Well, those guys, right? The question was, what is the hybridization state of that nitrogen? And the nitrogen had a sp2 hybridization state. Why? Because it had delocalization of the electrons. And if it did that, that means it has overlapping pi orbitals, which means that it's got a double bond, which means that you can't spin around those single bonds between the nitrogen and the carbon, right, of the amide, right, of the amide bond. Now, if it were actually sp3, then you could spin, right? But most of the time, it's going to be sp2 or it is sp2 because of the overlapping orbitals, which is pretty cool. Pretty cool. It actually makes the polypeptide chain, semi-rigid. Okay. Oh, skipping ahead. I always do that. Constitution isomers practice. 180-degree rotation along the C3C4 bond would make it more obvious that these two compounds are the same. So what they're talking about right here is from the previous slide I was talking about, when I was showing you that they were the same compound. They're saying if you rotate about the C3C4 bond, it would look the same. That's this bond right here, which makes sense because that's this bond right here. And if you were to rotate that bond around, right, that means that it's not pointing this way anymore, carbon 5. It's actually pointing up like this now. Look at that. It's the same compound, just kind of sideways, crooked. Okay? Then you can also name it to make sure 3-methylpentane, same thing. Right? Seal builder 4.6 on Wiley Plus, just for you. And you can see that in this chart where we have carbons that are between carbon chains that are between 1 and 4 are have a boiling point range fraction of below 20, right? That's like natural gas, of course, because propane is your propane tanks in your grill, or methane in your natural gas for your stove. Carbons that are 5 to 7, like pentane through heptane, have a boiling point range of fraction between 20 and 100 degrees. Those are solvents like ethanol, acetone, things like that, isopropanol. If you're a heptane to a dodecane, right? I've just confused something here. Is dodecane 12 or is that 20? Didecane? Yeah. One of those things I don't think I need to remember. Anyway, if it's 5 carbons to 12 carbons, right? That's like gasoline. Like octane. Isooctane is gasoline, right? It's got 20 to 200 as far as boiling range of fraction in Celsius. Kerosene and jet fuel, that's 12 to 18 carbons. 200 to 300. And then 12 carbons or higher. We got heating oil and diesel. They're 200 to 400 degrees Celsius. And then when you get to 20 carbons or higher, right, you have the non-volatiles, right? For example, lubricating oil and grease. And you have the wax and asphalt and tar, right? They're non-volatile, so they're not going to combust, for example. Okay, they're not going to just combust. See, that's actually one of the most common misconceptions, that volatility means that that it's going to explode, but actually that doesn't what it mean. That's not actually what it means. Volatile means it's going to evaporate. Right, so these don't evaporate at very low temperatures. Okay, so be clear about that. Next, sources and uses of alkanes. Right, so gasoline is a mixture of straight, branched, and aromatic hydrocarbons between 5 and 12 carbons long. Right, the main component of gasoline though is isooctane. Right, that's why when you go to the gas station and it gives you those numbers like 87, 91, 93 or something like that, those are octane ratings, isooctane ratings. Large alkanes can be broken into smaller molecules by cracking, right? So here the cracking is occurring, right, with some really high heat, really high heat, right? A lot of pressure and hydrogen gas, some reduction, right? Straight chain alkanes can be converted into branch alkanes and aromatic alkanes through reforming. And then after using these processes, the yield of gasoline is about 47% rather than 47% rather than 19%. Good old gasoline. It's getting more expensive these days. Oh, man. Okay, so now that we're done with naming things, we've got to talk about conformations and Newman projections and stuff. which is actually kind of exciting because I have like visual aids this time. Okay, visual aids. So first thing to recall is I said before you can rotate bonds around single bonds, right? So you can rotate substituents around a single bond, right? And it results in multiple 3D shapes called conformations, okay? There are various ways to represent a 3D shape of a compound, which you already knew that. Where you have the wedge and dash, right? Where the solid wedge here means that it's coming towards you, whereas the dash wedge means it's going through to the back of the paper, right, or the whatever it's sitting on. And then when it's just a straight line, it's in the plane of the paper, okay? You can draw it as a sawhorse, right, where it's kind of like a 3D structure, right, 3D drawing here, where your sigma bond is right there, and then your, and this is of course a, the example here is ethane. And the first carbon is sitting right there, and the second carbon is sitting right there, and you can see it three-dimensionally, right? But we like to use what we call the Newman projection, where we actually look down the axis of the central bond, right? The single bond that you're rotating around, right? These are called the Newman projections, and this is when I get to break out some different visual aids, okay? So let's take a look at this here, right? In a Newman projection, this is your eye, and you're looking straight down. All right, you're looking straight down the looking straight down the axis in which the rotation is about to occur. The carbon-carbon single bond in which rotation is about to occur, right? And so when you look at it from the front, and it's staggered the way it is, you can see that the hydrogens that are red are the ones that are in the front, and the hydrogens that are blue are in the back, right? You notice this because you see the bonds of the front hydrogens first, right? So let me change the view here real quick so you can see what's going on. And then, that's okay, you can just see it here. So this is a ball and stick model right here of ethane, right? And I know you can't see this very well, or and you can't feel this, and I doubt any of you actually have any of these at home, right? So the thing that I did but I did provide for you here, there's a digital way of seeing it because we are all so connected these days, right? So let me end the slideshow real quick. Okay, and then we should pop up like that. That's good. And then I want to minimize my PowerPoint so I can show you this. Okay. So this is actually a website called QR Chemistry. What is it called? Yeah, QRChem.net. Okay, and what you can do here is you can visualize molecules in 3D, which is kind of cool. And then if you're really, really rad about these kinds of things, you can actually send your friends a QR code so they can see it too, right? So the way you do this is it's really easy. It looks like I had these ready for you, but I guess they timed out, so I'm gonna have to do this again, right? You want to find a molecule. So the molecule that we're looking for here is ethane. So I would type in ethane here. Oops, sorry, wrong keyboard. Too many computers around. Let me see here. There we go. Type in ethane and hit enter. And I spelled ethane wrong, of course. Ethane. There we go. So ethane's easily found right there, right? And here's the molecule for ethane right there. And I would hit the submit button. Okay. And now you can see the QR code for ethane. Now, if you go to if you use your phone, if you have your phone with you, you can go to your phone's camera and just scan that QR code, and it will take you straight to the ethane I just made. Okay, so it's that technological, right? Not technological. So let's scroll up a little bit, and here's a stick drawing of ethane. So I want to actually turn on the ball and stick, not just stick alone, and that's what ethane looks like. So that's what I have here, okay? The only disadvantage that we have when using the digital version instead of using the actual ball and stick model that I have here is that you can't rotate around the bond, right? But at least you can see in the 3D model, right, how these things look, right? So you can zoom in on this. You can also rotate it around. And so when you rotate around this thing, this 3D model, and look straight down that center axis bond, right? That's sigma bond right there. It looks like this, right? It looks like that, okay? Now, if we go back down and look at our picture from our PowerPoint, which I've got to open up. No, that's not it. There it is. And let me go ahead and can't see what I'm doing. This way. There we go. And let's go ahead and make this part smaller. There we go, right? Looking at the slide there, right? Notice that when you're looking down the axis of the bond, right, of the single bond right there, what you see is right, is this hydrogen, the red hydrogens, right, in front of you, which is what you see here in like my screen, like you're looking at right now. There we go. Focus. Focus, camera. There we go. Focus. Right? So looking down the bond. Right? I'm trying to get to focus. There it goes. Focus. Focus, 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 focus. There we go. And so when you're looking down that bond, you can see that the hydrogens, right, are in this way. Sorry, it turned on me. But you have that hydrogen, the front hydrogen at the top. So I'll turn it this way so you can see it better. There we go. Right? So you can see that the hydrogen right here, right, the one right there that you're looking at right now down that bond, the carbon bond, which is this guy right here, is this hydrogen right there, right? And then this hydrogen right here is this hydrogen right here. And then this hydrogen right here is the one that's on this side. Not this side, sorry, this side. Wait. I'm looking at it backwards, so it's hard for me to tell which one's which. It turned again. Dang it. No wonder it's getting confusing. That's how you know that you can rotate around the single bond, right? Like that. See? You can rotate around the single bond. But the point is, looking down the axis of that single bond, you can see that the hydrogens in the front and the hydrogens in the back, right, they're kind of staggered. And you can see them in between each other, just like you see them in here. All right, just like you see them in here. Okay? The interesting thing about these things too is that if you were to show, if you were to switch this bond out here and put a double bond in there, you wouldn't be able to twist it this way. You wouldn't be able to rotate it. So these molecular model kits are actually very accurate to how we look at Newman projections and such. Okay. So going back to the QR code or QR CHEM thing, which is under here, I think. Yeah. See, same thing there. There's the front carbon that you're looking down right there. There's the hydrogens, right? And then the hydrogens in the back are those right there, right? So that's a Newman projection, okay? I'm going to be going back and forth between the PowerPoint a lot, so be prepared for that. Be prepared for that, okay? So let's minimize our QR CHEM real quick. Go back to this and start the PowerPoint again. There we go. Okay. Right, so again, you can see how looking down the axis of the single bond right there. You can see how it rotates, and you see how the hydrogens all on the carbons can rotate around this bond axis, right? And you can get them to be staggered, right? And there's actually implications for that. Before we go to those implications, make sure you check out Skill Builder. Whoops, back up. I always forget to, when I go into PowerPoint, I always forget to do my change my thing to draw. There we go. So before we move forward, make sure you go to Skill Builder 4.7 to practice drawing Newman projections. Okay. So the next guy we're going to look at here, right, another example of a Newman projection, is this 2-chlorobutane, right? It's 2-chloro because the chloro is on the second carbon right there, right? 2-chlorobutane. So I have that built right here too, okay? And if you want to be able to see it three-dimensionally, I can switch over to that in just a second. But in this case, what we're doing is we're going to look at it like this. So this is what it looks like over here. Over here, we're looking at it like this. Wait, hold on a second here. It's I see myself in like the preview of the video, but I can't like tell where I am. Like, it's crazy. So me looking at it right now from the front, right? That's what it looks like to me, right? When I'm looking at it front. So what I need to do is turn it around so you can see it the way it's supposed to look, right? Which is like that. Okay? So the carbon that you're actually looking at, the carbon that you're actually looking at, right, is going to be this carbon right here. You're looking straight down this carbon right here, right? And through its bond, right, to see the chlorine in the back. Okay? So we can rotate that around. The chlorine is in the back, like this, okay? And now the chlorine is at the top, right? There we go, the chlorine's at the top. Okay? Notice that the chlorine is at the top, and the methyl group, right, is no longer, notice that the methyl group here is a dash wedge, so when it was laying flat, it was going towards the paper, not going towards you, right? But now the methyl group is on the left side, right? And then the hydrogen that I was holding onto is on the right side, right here, right? Can you see it right there, right? And then in front of it is the other two hydrogens in the front, right? The one that you're looking down right now, and then the methyl group at the bottom, right? So that would be a Newman projection then of a 2-chlorobutane, right? And we can switch to the other view so you can actually see it digitally here. You go that way here. Oh, so you can see right down, right there, right? Good stuff, right? Good stuff. Yeah, there we go, right there. And I'm holding onto the hydrogen that's coming out the left side, right? So anyway, so you can go to CHEM again. And we can type in see, I guess it timed out, so I have to go create it again, but that's okay though, because it teaches you how to use this thing, right? Use your naming conventions and your rules to name the molecule. That was 2-chloro. Uh-oh, what happened there? There we go, sorry about that. There we go. So use your naming conventions, right? And go to type in the name of the molecule that you just saw there in that example, which was 2. Oh, wrong keyboard. That's what happened. 2-chlorobutane. There it goes. Shows up right there. And then we can see it there. Hit submit. So if you want to go straight to seeing it on your phone, use your camera and just scan that QR code right there. If you need to pause the video, feel free to pause the video. But here it is, 2-chlorobutane right there. We'll change it to ball and stick, right? And we're going to look at it straight down the carbon that the carbon that it's saying to do in the PowerPoint presentation in the lecture, which is this one right here, right where it's in the back. But notice, since we're not able to actually rotate the bonds on the 3D structure, right? On the digital structure, the methyl group's actually pointing towards closer to the chlorine. But if you see here on the ball and stick model, you can rotate it back and forth all the way around. Okay, and so with the chlorine in the back, right? With the chlorine in the back, the 3D structure here, the 3D model here, right, has the methyl group going like this. The methyl group in the front going like that. But it can rotate around, right? And so in the PowerPoint, it actually had the methyl group going down that way. So that should demonstrate to you how you can do a rotation around the sigma bond, right? The single bond, quite easily, okay? And there'll be implications for that in a second. We'll talk about that in just a second. But again, if you need to go ahead and scroll, not scroll, but see this on your phone, scan the QR code, and it'll go straight to your phone. You'll find the molecule we just built there. Okay, so let's go ahead and switch back to PowerPoint presentation view. Coolio. And then I will switch back to normal. There we go. So this is the next slide, conformational analysis. Okay, so back to looking at the ethane, right? Their conformational analysis means that you can actually, their specific names for where the rotation occurs or how the rotation occurs, right? So when you look down this angle right here, right, again, just like you see on the screen right now with that drawing, right there, it's talking about a dihedral angle or a torsional angle, right? Which is the angle that the hydrogens are at from front to back, right? So when I have it like this and the hydrogens are staggered, right? What it actually is, what is the dihedral angle? It's the angle between this hydrogen and this hydrogen right here. So this angle right here, right? This angle right here. I'm actually going to make myself larger so you can see what I'm talking about. Okay, so here's the staggered hydrogens. Okay, and I'm going to actually hold it down here so I can see it better. There we go. The staggered hydrogens, right? And so the dihedral angle or the torsional angle, right, is when you have them staggered like that, where you can see both the front hydrogens and the back hydrogens, right? It's the angle that's between this hydrogen right here, the one that's on the side, and the one in the back. So you see this angle right there that I'm pointing at right there? That's the angle we're talking about. That's the dihedral angle. Okay? And right there, you can see where my Apple Pencil is going straight down. That's dihedral angle. Okay? So the dihedral angle then for the ethane being staggered like this, right? That angle between the two hydrogens from the front and back carbons, right, is 60 degrees. Whoops, I always forget to do that. I always forget to put in my drawing thing. I've got to switch to drawing mode here. It's 60 degrees, right? And this makes a lot of sense. You know why it makes a lot of sense? Remember that you had the trigonoplanar guy, right? Geometry. And in trigonoplanar geometry, the angle between those two bonds right there, right, was 120 degrees. Whoops. Was 120 degrees, right? Well, if you imagine then turning it so that you can see down the angle, this right here, right, those two bonds right there, just right there, right? That's the same thing as a trigonoplanar thing, right? And that's 120 degrees right there. So if you split in half to have the hydrogen staggered right equally between those two front hydrogens, what's half of 120? That's 60 degrees. So that's where you get the 60-degree dihedral angle oil. Okay? Good stuff. Next. All right. Oh, I skipped ahead. So here's some names of some conformations, right? And the one that we've been doing the entire time now is called the staggered conformation, where when you have the hydrogens in between each other just like this, that's called the staggered conformation, and it's the lowest energy, right? Whereas when you have it so that the hydrogens are like this, right, and you see them like right behind each other like that, not in between each other, that is the eclipse conformation, which is the highest energy, right? And that makes a lot of sense because when they're this close to each other, there's like steric hindrance and there's strain, right? The electrons are all bumping into each other. The atoms are all bumping into each other. They're very close to each other, right? So they want to be at the lowest energy, and so to get themselves as far away as possible from each other, they stagger themselves, right? Instead of being eclipsed, right? So the difference in energy between these conformation, right? These two conformations is the torsional strain. The strain of wanting these hydrogens wanting to be as far away from each other as possible. That difference is actually 12 kilojoules per mole, right? Let me write that out because it's a little bit blocked. 12 kilojoules per mole. Okay? We can take that a little further here and put it on a chart, right? And when we have the dihedral angle, right, at 60 degrees, which is the lowest energy, right, when they're staggered like this, right, the potential energy is at its lowest, right? And when you rotate it, okay, and it gets closer and closer and closer to each other, right, where the dihedral angle right here is getting smaller, right, this dihedral angle right here is getting smaller, just like it is on this chart right here, right between 0 and 60, right? Look what happens. The energy jumps up again, right? And when it jumps up, how many kilojoules per mole? 12 kilojoules per mole, as we saw on the previous slide. So when they're right front and back of each other like this, they're eclipsed that way, right? That's a 12 kilojoule per mole increase in energy. Doesn't like that, okay? Then we can rotate some more, and we get closer and closer to 60 again, like we're going over here, right? Going this way, right? And we're back down to 60 degrees of dihedral angle, okay? And we're down to 60 degrees dihedral angle. What that means then is that we're at our low energy again. And then we can rotate some more, all right? And then we go back up again, right? And we're at the top now, okay? We're at the top now when we're at 120 degrees of dihedral angle right here, right? This is 120 degrees dihedral angle, right? So you can rotate this around infinitely, and as you progress between the eclipse version, where you have the highest energy, and then you go down in energy as you go towards the staggered version, and you get the lowest energy, right? So the most stable conformation then for an ethane is what? Is it eclipsed, or is it conformational, or is it staggered? It's staggered, right? With the dihedral angle of 60 degrees. It's not when it's eclipsed and the dihedral angle is 120 degrees because the hydrogens are right in front and behind each other. Okay? Whew. That was a lot of talk. It's possible the eclipse conformation is 12 kilojoules per mole less stable because the electron pair repulsion between the eclipsing bonds is 12 kilojoules for each eclipsing interaction, right? And since there's 3 of them, that's 3 times that they're going to pass by each other, right? as they rotate around, the total cost is 12 kilojoules per mole, right? 12 kilojoules per mole. That's where we get that from. What that means then is that 90%, 99% of the molecules of ethane, 99% of the molecules of ethane are going to be in the staggered conformation when you have them at the in room temperature, right? Let's take a look at this from the molecular orbital perspective, right? The difference in energy can also be rationalized by the presence of stabilizing interactions in the staggered conformation. So a filled molecular bonding orbital, right, has a side-on-side overlap with an empty antibonding orbital, right? That makes sense. Because here you have the molecular bonding orbital, right, of one of the hydrogens, okay? But when the other two hydrogens are pointed down, when the other hydrogen on the other carbon is pointed down, straight down, so it's opposite the one from the first carbon, right? Then its antibonding orbital is actually in line with the bonding orbital of the carbon in front of it, of the hydrogen in front of it, right? So now you're overlapping a bonding molecular orbital with an antibonding molecular orbital, which is good because there are no electrons in an antibonding there are no electrons in an antibonding molecular orbital, right? So there won't be as much electronic repulsion, right, between these two things. But if you rotate this thing around, right, and then you put a bonding molecular orbital there, what happens? Now you have two bonding molecular orbitals right next to each other, both filled with electrons. They're going to be repulsing each other like crazy, right? So crazy, it's 12 kilojoules per mole. Crazy. That's how I say kilojoules. Kilojoules per mole. Crazy, right? Okay, we can do the same kind of thing with propane. So again, I have here a visual aid, and this is propane, right? This is propane right here. And I want you to be able to see it three-dimensionally on the CHEM thing, but since they're timing out, I have to go through and like search for them. It just takes a lot of time. So you guys go through qrchem.net, search for propane, and do this yourself. Right? You can even use you QR code one of the ones I've already done for you on the lecture, and then just create another one, and you can do another one and type in propane. So this is propane right here, right? And the way we're looking at propane here is we'll have the methyl group in the front. So for you guys, it will be like this, right? Propane will be like that, okay? And now it's rotating like this, right? With the methyl group going around the sigma bond, right? Okay? Because we're looking down this carbon bond right here. And you can do it from this side too. It doesn't matter because it's symmetrical on both sides. But let's say we're looking down like that, and it's rotating around, okay? So having a methyl group in there is also even more steric hindrance, right? There's even more repulsion going on here, okay? And that's why you see that the number now is 14 kilojoules per mole, not 12 kilojoules per mole, okay? So same as before, as this thing spins around, as that methyl spins around, it comes in contact. The hydrogens here and the carbons here, the carbon here comes in contact, right, with the, not comes in contact, but it's electronic repulsion comes in contact with the electronic repulsion of the carbon behind it, right, and the hydrogens behind it, and it starts repelling itself, right? It starts repelling itself. And so, just like in the ethane, the most stable and the lowest energy conformation would be staggered here, right, for the propane, where the methyl group is in between, right, like that. It's in between, right? It's sitting in between. I'm trying to make it so I can see it like you guys here. And I'm going to go ahead and do a full headshot there, right? Where it's sitting in between, like that. There we go. All right. It's standing straight up right here in between these two hydrogens in the back, right? And you can look down the dihedral angle, right here, right? And the dihedral angle right there is 60 degrees, right? As it rotates around and starts eclipsing the hydrogens like this, right? We jump all the way up to 14 kilojoules per mole higher, right? Because of the torsion strain, right? So propane's torsion analysis, right? The analysis of propane's torsion strain is very, very similar to that of ethane. Okay. Whew. It's tough doing this on video. Like, it's way easier when you're in class and you can just pass the freaking thing around, you know. So anyway, let's go back to the presentation. Okay. Conformational analysis, propane and energetics. Okay, so the barrier of rotation for propane is 14 kilojoules per mole, which is 2 kilojoules per mole more than ethane. And that makes sense, right? If each of the hydrogen-hydrogen eclipsing interaction costs 14 kilojoules per mole, 4 kilojoules per mole of stability, that total can then be subtracted from the total 14, right? And it's calculated to calculate the contribution of the actual methyl group hydrogen eclipsing interaction. And so what that means then is that as each hydrogen passes each other in eclipsing, right? We already know that's 4 kilojoules per mole from the ethane example, right? Then the question is, then what is the interaction for what is the energy cost for a hydrogen being eclipsed by a methyl group, right? Well, it's easy because we already know experimentally that 14 kilojoules per mole is the total cost, right? Add 4 plus 4 for the two hydrogens and then subtract, and then you get 6 kilojoules per mole. So every time a methyl group passes and eclipses a hydrogen, it costs 16 kilojoules per mole, right? So again, this is one of those examples, just like in ethane, where the staggered is the most energy stable conformation. Okay, another example here, we have butane, and I have butane again right here. Okay, butane's a little bit different because now you have two methyl groups that are going to be passing each other, right, when the sigma bond rotates. Okay, so in this very first structure here, right, the two methanes or methyl groups, right, they're very close to each other. Okay, they're very close to each other. They're like that. Okay. Of course, I don't know why I jumped to that structure. Let's go ahead and do this structure. There we go. The actual first structure here, right, is the two methyl groups completely opposite of each other, right? Completely opposite of each other. And as the two methyl groups rotate, right? As the two methyl, as the carbons, as the single bond rotates, right, and the methyl groups get closer to each other, like it does right here in the second structure, right? That's a 16 kilojoule energy cost, right? That's a 16 kilojoule energy cost right there. Okay, 16 kilojoule energy cost. Then, right there, like that. Okay, like that. So right now the dihedral angle right there is 120 degrees, right? So interestingly, it's different from the propane and the ethane because this time the lowest energy is at 180 degrees dihedral angle, right? That's 180 degrees dihedral angle when the methyl groups are completely opposite of each other. But then when it goes to what we would think would be staggered, right? Something like that, right? There's actually some eclipsing occurring between the hydrogen in the back and the front methyl, right? And so that actually is the 16 kilojoules per mole cost when it does that, right? It's getting closer to the methyl group, right? But really right now it's interacting with the the hydrogen behind it. Okay, and then as it goes away, moves away from the hydrogen, the methyl group rotates away from the hydrogen, right? We jump back, we start going down, right? And now there's only a 3.8 kilojoule per mole difference, right, between what it is right now and what it was when it was 180 degrees dihedral angle, right? Okay, so that was the that was the 60 degree dihedral angle right here. Then the energy, torsion strain, is way up. It skyrockets now, right? Because now the two methyl groups are eclipsing each other, right? They're eclipsing each other. And I'll show you this in big screen here, right? They're eclipsing each other right here, right? One is right in front of the other. See, there's the bond that we're looking down. And they're eclipsing each other, right? And then now right now the dihedral angle between the two methyl groups is 0, and the energy just shoots up like crazy by 19 kilojoules per mole. Okay, and then it moves away, right? And you didn't see me write that, but it shoots up by 19 kilojoules per mole. And then it starts to move away, and as it moves away to 60 degrees, right there, right? As it moves away to 60 degrees, like that, right? The energy starts to go down again. It gives us a little trough that we saw right there, right? This little trough right here, okay, at 60 degrees. That trough at 60 degrees was just 3.8 kilojoules per mole higher than it was when it was all completely opposite of each other, okay? And then it starts to shoot up again. Why? Because now it's getting close to the hydrogen that's behind it too, like that, right? Whoops. I'm trying to change it so that you can see it. There we go. It's getting close to the hydrogen that's behind it. This one right here, right? There's the front methyl group. It's getting close to that hydrogen behind it right there, right? And so it shoots up, right? Another 16 kilojoules per mole, right? Where now it's completely eclipsing the hydrogen that's behind it, okay? And then it goes all the way back down to its most stable, right? When the dihedral angle between the two methyl groups is 180 degrees again, right? And I'll switch over so you can see what that looks like again. See, and now it's at 180 degrees from each other. Good stuff, good stuff, okay? Whew. So this is just showing in pictures what each one of those look like, right? And the kind of steric strain that's involved, right? Steric strain. Steric strain is like what I was talking about before, where you have like electron repulsion, and it's making it so that it doesn't want to be close to each other, and it needs to be as far away apart as possible on the same molecule, so that it can achieve its lowest amount of steric strain, so that it can be at the lowest energy, right? So the stability of sorry, I forgot to switch it back. So this is the conformational analysis of butane in its steric strain, right? The stability of the different staggered conformation differs by 3.8 kilojoules per mole, which you saw on that chart that we just went over. When the methyl groups are gauche, so gauche, right here, right? That's when we were seeing it at 60 degrees. And I'll show you that real quick. I'll switch back. So right now it's at 180 degrees, okay? When the molecule is being in gauche conformation is when they're like this, right? And the dihedral angle between the two, right there, right? Sorry, focus. There we go. The dihedral angle between the two is 60 degrees, right? That's gauche. Okay. Methyl groups experience a gauche interaction. That's why we call it gauche, right? and it can be gauche on both sides, right? We had the gauche that was over here, right? We had the gauche that was on this side here. Stay there, focus, right? We had the gauche that was right. There we go. We had the gauche that was when it was right here, right? 60-degree dihedral angle, and then it can go this way, right? Again, a 60-degree dihedral angle, and that's also gauche. So there's two gauche positions. Gauche positions, right? And then we have the anti-position, right? And the anti-position is what you saw when we first started all this, when it was at its most stable, with it being at 180 degree dihedral angle, like that, right? 180 degree dihedral angle, right? And the methyls are opposite of each other, right? Still on the same, rotating around the same sigma bond, right? But they're opposite each other, and that would be anti. Okay. Whew, okay. The highest energy conformation for butane results when the methyl groups eclipse one another, which we saw that when I was going through the the molecular model kit, right? Or the model that we built, the 3D model that we built. Okay, so let's calculate what kind of energy is what kind of energy cost it is for the two methyl groups, right, to pass each other. Okay, so we already know again from before that when two hydrogens pass each other, when they're rotating around that bond, right, it's 4 kilojoules per mole, right? 2 times, that's 8 kilojoules per mole. We know that the total experimental kilojoules per mole cost for when the methyl groups eclipse each other is 19 kilojoules per mole, right? So the actual, we know that the total cost of the entire rotation, right, costs 19 kilojoules per mole, right? So if we subtract the 8 kilomoles per joule from the hydrogens passing each other from the total 19 kilojoules per mole of the entire rotational act, right, then we can calculate what it costs just to have two methyl groups passing each other, right, like this, passing each other, eclipsing each other like this. So each time a methyl eclipsing interaction occurs, that's 11 kilojoules per mole. That's a lot, right? That's a lot of torsional and strain, steric strain. Okay, so now we just have a little chart here, and comparing the different energies involved in the energy costs involved in the rotation of that sigma bond. Okay. The energy costs for eclipsing and gauching interactions can be used to approximate the energy of a given conformation. Okay. So here you see the two H's, hydrogens, when they eclipse, only 4, right? That's a torsional strain. So torsional strain is just the strain of the actual rotation. Okay, because like it's kind of like torque. Right, when you're talking about torque, like in a drill or something, and it's the amount of rotating, right? So the torsional strain is actually just the energy involved in the rotation of the bond, right? So when it's just HH, right, two protons eclipsing each other, there's only torsional strain, and that's 4 kilojoules per mole. Then there's the methyl proton eclipsing. It's still just torsional strain because the proton is still kind of small, right? And then the methyl is going around, right? There's a little bit of kind of like a repulsion occurring there, and that's why it's 6 kilojoules per mole. But then when we get to the eclipsing methyl groups, right? That's a combination of both the torsional strain, right, and also the steric hindrance, meaning that these molecules are just so big, right, and they're coming so close to each other that they don't want to be, and that just increases their energy a lot, right? because they're so big and that they're sterically hindered, right? They're just, that's what that means. Steric hindrance. That steric hindrance costs 11 kilojoules per mole. And then we have the gauche. That strain is going to be the steric interaction, right? Again, or steric strain again, where when it's gauche, right? Again, these two substituents are just so big that they don't want to be so close to each other because it causes more repulsion, right? From their electron densities and all that, right? That at gauche, right? It's mostly not even torsional strain; it's just steric strain, and it's at 3.8 kilojoules per mole, right? So practice with skill builder, 4.8 to identify relative energies, right? When you're doing Newton projections. Okay. That ends today's lecture. So today there's actually a quiz, right? Quiz 3, but we're not done yet with alkanes and cycloalkanes. So there's not an assignment assigned for today, right? There's no assignment assigned for today, but that quiz is still assigned, and it's due tomorrow at 7:59 a.m. And tomorrow is June 9th, 2021, right? Yes. And then reminders, you have exam 2 on Friday, 6/11/2021, right? And then also another reminder is that today your aspirin and other analgesics lab will be assigned today. So I will see you in a few minutes for pre-lab lecture.